So hello and welcome guys. In previous video we have talked about the generation, transmission and distribution of the power system, and in which we have seen that how the power is generated at remote area and how it is transmitted to at high voltages and how it is distributed and it is reaching to our home. In today's particular video we are going to discuss about the transmission. Here in the transmission network, right, in the transmission network we are going to see that why is that so to go for high voltages, right? Why we are using high voltages for transmission, and till what voltage we can go, right? Till what voltage, right? So in today's session we are going to answer these two questions, and this is the basically second video in the power system series, and if you have not subscribed the channel, please subscribe it, and let us start the video. Okay, so we have discussed in the previous video that a power is generated from a generation station and then it is transmitted to a particular load, right? And this load is basically our homes, it could be industries, right? It could be industries or it could be agriculture, right? So these are the loads we have, and we will also discuss about the loads that we have in a next video. Particularly the thing over here is we are having the transmission and the distribution, right? And in which we have seen that transmission is done at high voltages. जो transmission हो रहा है वो high voltages पे हो रहा है, and जो distribution हो रहा है वो particularly less voltage पे हो रहा है compared to the transmission. So in today's video we are going to focus on that why we are going for high voltages and what are the different reasons for it. Also we will see that if we are going for the high voltages, then till what voltages we can go in the transmission network in India, right? So that thing we will focus in this particular video. So for that let us take a particular system, right? So in which let us discuss that we have a system, we have a multi-phase system. Basically in India we have three-phase system. In three phase we are transmitting the power, and in some cases we may have the six phases also. Three phases are going parallelly. So basically we take an example in which we are transmitting P power, right? So P is the power that is delivered for and this is per phase power, right? Per phase we are delivering P power, right? And we are taking the example for N phase. So here we are talking about the P is basically a per phase power. Similarly V, that is our per phase voltage, and the I is per phase load current, right? Or this is the current that is flowing through the transmission lines. Similarly cos phi is our power factor. Then we have resistor, that is resistance per line, or that is resistance of conductor, right? And the value of this resistor is basically, we know that it is rho L by A, right? Where L is basically length of the line, A that is area of the conductor, and delta that is rho, sorry, there is rho that is basically resistivity of the conductor material. Okay, so now we need to see that the power that is delivered, right? The power that is delivered is basically, we can give the equation that is Vi cos phi, right? The power that is delivered, that is P is equal to Vi cos phi, right? And this is basically active power. We are talking about the active power only. So here from this equation we can say that the current that is flowing through the transmission line, that is P divided by V cos phi, right? And this we will give the equation number 1 over here. And now we will talk about the power losses that is happening in the line, right? Power losses in line, right? And this basically per phase. Okay, So we will denote our power losses by omega W. So W is we can basically give the power losses by I square R. The I square R losses are there. So if we put the value of I over here, then we can definitely call it is P square divided by V square cos square phi into R, right? And R basically we know that R, that is rho L by A, right? So if we put the value of R, our W is going to be P square rho L divided by V square cos square phi into A, right? So this is our W. Okay. So now what we are going to do? We know that our current density, right? Our current density, that is delta, that is I divided by A. So from that we can also say that A is equal to I divided by delta, and if you put the value of I, we know that I is equal to P divided by V cos phi, right? If you put the value of I, then it is going to be delta V delta into cos phi, right? So this is the equation for A, right? And now if we put this value of A into our previous equation that we have for W, right, that is power loss, so we can say that W is going to be P square rho L, and that is V square cos square phi, and in place of A we are going to put P and V delta cos phi, right? So this V and V square is going to be cancelled out, cos square and cos phi is going to be cancelled out, P and P square is going to be cancelled out, right? And the final equation that we will have for the W, right, for W the final equation that we will have, that is P delta rho L divided by V cos phi, right? So this is the equation for power loss in the particular line. Right. So this is the equation of power loss, and this we will go with equation number 3. Right. Our equation number 2 was the area. Okay. So from this equation we can say that the power loss is inversely proportional to voltage. We'll talk about it later. First we will see the derivation. Okay. So we have derived the power loss in the transmission line. Now we are moving forward for the efficiency. Right, and here we are talking about the transmission efficiency, right? We are talking about the transmission efficiency, and any efficiency if we are referring to, that is basically output divided by input, right? And what we can say that our input is basically the sum of output plus whatever the losses that we are having in the system, right? So we can also call it our input as a output plus losses that we have in our system. Okay, so now if we talk about the output, right? Okay, so now if we talk about the output, that is output that we have is basically the power that is delivered at the receiving end. So similarly, and the losses that we have just derived, that is W, right? So our equation for the transmission efficiency is going to be P divided by P plus W. Okay, so now we know that P is basically P, and this is P. Okay, so here what we need to do, we need to put the value of W, and for W we have derived, that is we have in the equation number 3. Here you can see the equation number 3. The W is basically P into rho into delta into L divided by V cos phi, right? So the same thing we are going to put it over here. We'll put P into rho into delta into L divided by V cos phi. And if we simply take the LCM over here, right? If we take the LCM, then it is going to be P into V cos phi divided by P V cos phi plus P rho delta into L, right? And if we take the P common, so it will be V cos phi divided by V cos phi plus P rho delta L. Okay, and now our if we simplify this equation further, then finally we will end up with this equation 1 minus P into delta into L divided by V cos phi, right? If we simply further this particular equation more and more, then we will end up with this kind of equation. So our transmission efficiency is going to be this much, right? And this we give equation number 4. Okay, so now moving forward, we have derived the losses in the line, we have derived the transmission efficiency. Now we are going to derive resistance drop in the line. We are going to derive the resistance or a particularly IR drop or voltage drop per line, right? And that is basically I into R, right? I, here what we can do, we can multiply I and divide I, so we can say that it is I square R divided by I. Similarly, what we have done, we have multiplied I and we have divided the I. So this I square R, that is basically W, and in the denominator we have I. So if we put the equation of W, the equation number 3 that we have derived, we have derived the equation for W. So this was P into delta into rho into L divided by, we have V cos phi, right? And similarly for I, we know that I is equal to P divided by V cos phi, right? So if we put that thing, then it is going to be P into V cos phi, right? From this equation, this P and P is going to be cancelled out, V cos phi and V cos phi is going to be cancelled out. So at the end we have delta rho and L. So our resistance drop, right, or VI drop, right, or sorry, voltage drop is going to be delta into rho into L. Okay, and this is going to be our equation number 5. Now we are going to derive about the volume of the conductor that we have. Volume of conductor. Okay, so basically we have the cross sectional area, right, that is A, right, and the length of the conductor, that is L, right? So our volume is going to be A into L. Okay, so we have derived the equation for the A, right? Here we can see that, so our A is basically what, I divided by delta, and I is basically P divided by V cos phi, and into delta we have. So we can simply put A is equal to P divided by delta V cos phi into L, right? So this is going to be our volume, right? And if we see over here the delta, right, and if we see our W equation, W is basically P rho delta L divided by V cos phi, right? So simply from here we can get delta, that is W V cos phi, divided by, we have P rho and L. If you put the similar value over here in this particular equation, right, here if we put for delta, if we put W into V into cos phi divided by P rho L, then what we will get, the P into L, that is we have in the denominator we have V cos phi, so we will put V cos phi. Now we will put the value for delta, so here we put W into V into cos phi, and P into rho into L will go into the denominator, sorry, numerator. So what we will have over here, we have P square, we have L square, and we have rho. Similarly here we have W, V square, and cos square phi, right? So we have volume of the conductor, right? Just a minute, yes. So volume of the conductor, that we will denote with V conductor. So this can be given by this particular equation, and that is our equation number 6. Okay, so now we have derived this 6 equation, and let us just gather all these equations, and now we will get the conclusion from these equations. Okay, so we have these all equations over here with us, and now we are going to get the conclusions from these equations. So yes, we are dealing with the question that why high voltage is required, and now we have these 4 equations. From these 4 equations we can say that, here from the equation number 3 we can definitely say that if our transmission voltage is increased, right, so our the losses that we have in the particular transmission line, that is going to be decreased, because from the equation number 3 we can definitely say that W is inversely proportional to the voltage, right? W, that is our losses of the line, that is inversely proportional to the transmission voltage that we have. So similarly, if we are increasing the transmission voltage, our losses in the particular line is going to be decreased, right? And if the losses are going to be decreased, the transmission efficiency is definitely going to be increased, right? And that is our second advantage is, right? That is our second advantage of increasing the transmission voltage. Here you can see that from the equation number 4, that if the transmission voltage is increased, right? If the transmission voltage is increased, efficiency is also going to be increased, because it depends on this particular voltage, right? If the denominator, right, it's simply like that, the efficiency is 1 minus something constant, that is we call it k, and it depends in voltage into cos phi, right? So if this voltage is going to be increased, definitely this k divided by something is going to be decreased, right? K divided by, let us say, m. So the proportion is going to be decreased, and 1 minus k by n is going to be decreased, then efficiency is going to be increased, right? And in the similar logic, we can say that if the line losses are reduced, then efficiency is going to be increased. But mathematically we can say that if the voltage is increased, simply the equation of the transmission efficiency is this, and from this equation we can definitely see that if we have the higher transmission voltage, we can definitely have the higher transmission efficiency. So that is the second advantage of having the higher transmission voltage. Now if we can see that if here from the equation number 5, we can definitely see that the IR drop is constant, right? The IR drop is constant, and as the resistance drop per line is constant, and hence the percentage resistance drop will decrease with the increase in voltage, right? So percentage resistor drop is going to be decreased with increase in voltage, right? So that is the third advantage. And let me scroll down just, right? The fourth advantage is from equation number 6 that we have. Here you can see that the volume of the conductor that depends on the denominator of the voltage, right? It is, that means the volume is inversely proportional to the square of the voltage. So the volume of the conductor will reduce with the increase in the voltage. Right. So if the volume is going to be reduced, right? If the volume is reducing, that means what? We will get the lesser cost for that particular conductor that we are going to use to transmit our power. So similarly, we will use the material that we are going to use to make the conductors, right? And simply we will save so many money for if we are reducing the cost for the transmission conductors that we are using, right? So that will definitely help us to build the transmission network that is with the economical price. So that is also the fourth advantage that we have. And simply if we see this equation, from this equation we can definitely see that for a constant power, for a constant line, for a particular resistivity, for a particular power and power factor, we can definitely say that the volume of the conductor, right, that is inversely proportional to the voltage square, right? The square of the transmission voltage, right? So these are the conclusions that we have, and from this conclusion we can definitely say that if we are transmitting the power at higher voltage, then it will save us the money, it will save us the it will definitely help us in improving the efficiency. That means the drop that we are having, the losses that we are having in the transmission itself, it is going to be reduced. So definitely we should go for the higher voltages. Now with that, if we are going for the higher voltages, we will definitely have the disadvantages, right? So we'll talk about the disadvantages also. Disadvantages of having a high transmission voltage, right? So here we can say that if the transmission voltage is increased, the insulation required for the particular conductors, right, the insulation required between the conductors and the earth tower, right? Conductor and earth tower, between conductor and earth tower, that will also more insulation would be required, right? So first thing is more insulation is required, right? And this will definitely increase the cost of the line, right? The cost of line supporters, right? If insulation is increased, the weight of the conductor is also going to be increased, and the supporters that we have in the transmission tower, right? The transmission tower that we have, in which we have the supporters, right? We have the cross arms, the holders of the conductor, right? So that is also going to be, the cost of that particular equipment is going to be increased. So that is the first disadvantage. Now the second disadvantage is, with the increase in the transmission voltage, right, more clearance is required between the conductors and the ground, right? So second disadvantage is more clearance is required, right? And if the more clearance is required between the conductor and the ground, that means what? We need, you know, we need the tower with higher height, right? So that is the second disadvantage. If we talk about the third disadvantage is, with the increase in the transmission voltage, more distance is required between the conductors, right? These conductors, they should have the proper distance between them, so more distance is required between the conductors, right? And that means the longer cross arms is required, right? That means what we have is, we have longer cross arms, right? So these are the disadvantages. Of course, there are corona and all other stuff, proximity effect and all other stuffs are there that we will discuss, right? But for a particular extra high voltages, this is the direct disadvantages that we will have in our system, right? So the question that why we are transmitting the power at high voltage is being answered, and in that we have also discussed the advantages and the disadvantages that we will have. Now the second question that we have in our mind is, yes, we have cracked that we want high transmission voltage, right? We want high transmission voltage, right? That we want, but till what value we should go, right? Till what value can we transmit the voltage at 1100 kV? Can we transmit the voltage at 1200 kV, right? Should we go for 100 kV, 200 kV? What is the particular value, right? So that we need to discuss over here. So basically, if we talk about the transmission, right? So to transmit, right, if you want to transmit the power from one end to other end, right? So we have so many costs involved in that particular thing, right? If we talk about the total cost in the transmission that is involved, right, at the time we need to figure out that what are the different cost for that. So बेसिकली कोई पावर एक जगह से दूसरी जगह ट्रांसमिट करने के लिए जो टोटल जो इन्वेस्टमेंट उसमें लगती है, तो दैट इज फर्स्ट थिंग दैट वी हैव इज कॉस्ट ऑफ ट्रांसफॉर्मर, right? Because we need to step up the voltage, so transformer is going to be there. After that we have switch gears, right? In the switch gears we have isolators, we have circuit breakers, right? We have bus bars, we have relays, right, etc., right? So these all things are also required, right? Along with that we have insulators, the cost of the insulators. Then we have lighting arresters, right? Plus we have supporters. Supporters, that means the tower that we have, cross arms, all the things have been covered in the supporters. After that we have the cost of conductors and the cost of erection also, right? So for, if we talk about the transmission, this all the cost we need to take into the account, right? So let us call it the capital cost for the transmission. Let me give the name, that is the capital cost for transmission, right? So these all things we need to take into account. Now we need to set a particular value that at what standard voltage we should transmit the power, so that this total cost, this capital cost is minimum, right? That we need to take into the account. So for that, what we can do, we can definitely what we can do, we can take one standard value of voltage, right? And for that standard voltage we need to calculate the capital cost for the transmission, right? And from this exercise, what we will have at the output, we will have a particular curve, right? We will have a particular curve that shows the capital cost in the y-axis, and here we will have the transmission voltage, right? So we may have this kind of curve, right? And from this curve we may observe that if we transmit our particular power at this VA voltage, at that time we have the minimum cost for the transmission, right? So we should transmit from for this particular voltage, right? So this is the one method we can do this kind of study, right? But on the other hand, we have to take into the consideration of the what amount of power that we are transmitting. We also take into the consider that till what distance we are transmitting the power. We also have to consider the weight of the conductors, right? And we also have to consider that what amount of load that is connected, which kind of load that is connected in at the particular end, right? So all these things, right? The power transmitted, right? That means the quantity, or let us say the amount, right? That is in the kVA, right? So we need to also consider the power. We also need to consider the distance, right? That is into the kilometer. That means till what distance we are transmitting the power, right? We also have to consider the characteristics of the load, right? So these all things we need to take into the account, and these things is not going to be answered by this particular method, right? So there is one appropriate equation for calculating the economical transmission voltage that covers these things also, right? And that is basically economical voltage, right? Economical transmission voltage, that is 5.5 into kilometer divided by 1.6 plus load in kVA divided by 150, right? So this is a one equation that covers the distance. This covers distance as well as this covers the load, or that means the power that is transmitted. See, when we are designing a particular voltage for transmission, these two things we cannot ignore, right? These two things have a considerable amount of equivalence in the economics of the transmission voltage, or into the economics of the particular cost that we have to transmit a particular power, right? So we cannot ignore these two parameter. So here what we can see that if we increase a particular distance, then cost of the terminal apparatus is reduced, right? If we increase the distance, the cost of terminal apparatus is reduced. And in similar way, if we increase the amount of power that we are transmitting, right, the cost per kilowatt of the terminal station is also going to be reduced, right? Cost per kilowatt of terminal station, right, it is going to be reduced, right? So these are the things that we need to take into the account, and this equation is also going to help while designing a economical transmission voltage, right? And similarly, if we talk in generally the voltages that is occupied for the, or that is adopted for the transmission, right? That in India that we have, it is for 15 to 30 kilometer, we have the transmission voltage that is 11 kV, right? For 30 to 60 kilometer, the transmission voltage that we have, that is 33 kV. Similarly, if we go for 60 to 100 kilometer, we prefer to transmit our power at 66 kV. If we want to transmit the power from 100 to 200 kilometer, then the preferable transmission voltage is 132 kV. Similarly, if we are choosing from 200 to 300 kilometer, right, then we may go for 220 kilowatt, and similarly from 300 to 400 kilometer we can go for 400 kilowatt also, and if we are going further then we can also go for 765 kilowatt, right? So if we see from this particular data that we have is the general transmission voltage in India, right? That is basically 33, 66, 132, 220, 400 and 765 kilowatt, right? So these are the general transmission voltage that we have in India, and that too from 220 to 400 is mostly used in transmission network that we are having. So this is all about the voltages that we have, and also we have answered that till what voltage we should go. Basically, the amount of voltage depends on so many things. If we are going further, then it may happen that the cost of the switch gears may increase, or the cost of the conductors may increase, right? It depends on particularly so many factors are involved in deciding the transmission voltage. So this is all about the transmission, and if you want the lecture notes of this particular lecture that we have just discussed, then you can also find it, the lecture notes you can also find it into the description box. And thank you guys for watching this video. We are going to make a series on the power system that will definitely help you in cracking any exams. So stay tuned, subscribe the channel, and hit like if you have gained something from the video. Thank you guys.
कलेक्टर की फिजिकल साइज बहुत ज़्यादा है, ठीक है, तो 4 इलेक्ट्रॉन्स तक रिपल्शन फोर्स की वजह से जाएंगे, वहाँ पर उन पर काइनेटिक एनर्जी का जो इफेक्ट आ रहा है उसकी वजह से 100 में से 5 से 10 इलेक्ट्रॉन्स ही ऐसे रहेंगे कि जो बेस